Hello, my name is Charles Zona, and I would like to welcome everyone to today's McCrone Group webinar. Our presenter is Kent Rhodes of McCrone Associates. Kent is going to talk to us about using X-ray photoelectron spectroscopy, or XPS, for industrial problem solving. Before we get started, I'll give you a bit of Kent's background. Kent is the Senior Vice President and Technical Director of McCrone Associates. In addition to his management of technical services at McCrone Associates, he also performs surface analysis using XPS, secondary ion mass spectrometry, and electron microprobe analysis. Kent has also taught the Scanning Electron Microscopy course here at Hooke College of Applied Sciences. Kent will field questions from the audience immediately following today's presentation. This webinar is being recorded and will be available on the McCrone Group website under the Webinars tab. And now I will hand the program over to Kent.
Hello and good afternoon. Thank you for joining us today. My name is Kent Rhodes and I perform surface analysis at McCrone Associates. Surface analysis has been a passion of mine for more than 30 years, and I'm still fascinated by the chemistry that occurs on just a few outermost atomic layers of materials. And today I'd like to share you some background information on surface analysis and show you a few examples on how it can be used on industrial samples. I'd like to begin by defining some of the terms we will be using in today's webinar. So many analytical techniques have some surface sensitivity, but the techniques we're talking about today are really specialized for analyzing just a few atomic layers on the outermost surface of a solid material. And so we're talking about an analysis depth of only around 0.5 nanometer to 3 nanometers in depth. And there's a variety of different techniques you can use to probe these very thin layers on surfaces. But the one that's probably most widely used, and the one we're going to focus on today, is X-ray photoelectron spectroscopy, XPS. This is also known as ESCA, ESCA, which stands for Electron Spectroscopy for Chemical Analysis. And why this technique is widely used is it has some advantages over other surface-sensitive techniques. These advantages include you can analyze non-conductive samples relatively easily. It uses an X-ray beam to irradiate the sample, so you don't get as much charge buildup as if you used a charged particle beam. Also, the technique provides chemical information, not just elemental or structural information, and we'll see an example of that later in the presentation. And finally, quantification is relatively straightforward with XPS using standards. So the scope of today's webinar will be XPS analysis of industrial samples. So this schematic diagram illustrates the surface layers we'll be discussing. So when going from the outermost surface of a material into the bulk, you can define these various layers. So the surface, as we said, is just a few nanometers in thickness. And this is where atoms or molecules from the environment, whether they're in a gas, liquid, or another solid, can interact with the surface atoms of a sample. As we go deeper, we may have a region where what we would define as an ultra-thin film, up to maybe 10 nanometers in thickness. And some of these same analytical techniques can be used to probe an ultra-thin film. As we get deeper, we get into the realm of thin film analysis, and here you can use techniques maybe many of you are familiar with, including scanning electron microscopy and electron microprobe analysis. And then finally, as you get micrometers deep into a sample, you start to be able to use bulk analysis techniques like XRF to probe the material. So there's a couple key points here. First, surfaces can have very different compositions than the bulk of the sample. And that's really one of the main motivations for using these surface-specific techniques for the analysis. Also, because we are analyzing such thin layers, contamination can be a real concern, and this contamination could be from handling or production of the samples, or even the vacuum system that you're using in the instrument that you're using for analysis. So you really have to think about how the samples were handled and prepared in order to determine what information is appropriate and what information is important on your sample. And this can really be a concern with industrial samples that may not be handled as carefully as research samples in a laboratory. So what are some of the applications for these analytical techniques to analyze just the outermost surfaces of materials? Well, again, anytime two surfaces interact or a surface interacts with the gas or liquid, especially at room temperature, the initial chemistry is going to involve those outermost atoms exposed on the surface of the solid material. So applications such as adhesion, where you're trying to get two surfaces to stick to one another. Printing or wettability, where you're trying to get a liquid applied to a surface, will involve that outermost surface chemistry. And some reactions, such as oxidation and corrosion, may begin with the surface atoms and then proceed to have more and more atoms react deeper into a material. Other areas include catalysis. Most of these analytical techniques were first developed and applied to heterogeneous catalysis systems, where the surface chemistry is controlling the rate and the products of a reaction. Also, tribology, which is the study of friction and wear of materials, will be heavily influenced by the chemistry of the outermost surfaces of solid materials. And then, of course, for industrial applications, a lot of surfaces have to be passivated or have surface treatments applied in order to achieve the performance that's necessary. So how those surfaces are prepared and how they're treated are questions that can be answered by these surface analytical techniques. And then, of course, contamination. Many systems are very, very sensitive to very small amounts of contamination on the surface. Now let's talk about the instrumentation used for surface analysis. And again, we're going to focus on X-ray photoelectron spectroscopy. So this schematic diagram shows the layout of a Phi Quantum 2000 XPS instrument, and this is very similar to most of the commercial instruments available. The experiment involves irradiating a sample with an X-ray beam. So the X-ray beam is produced by hitting a target material with a beam of electrons, and typically aluminum X-rays are going to be the source. You can also use magnesium, zirconium, some other materials, but by far the most common source is aluminum X-rays. Those X-rays then are focused onto a sample using ellipsoidal mirrors, and this also produces a monochromatic source of X-rays. Those X-rays interact with the atoms of the sample to produce photoelectrons. The photoelectrons are then collected by a lens and sent through an energy analyzer to separate them out by energy. And this is used then to produce a spectrum of photoelectron intensity versus energy. So if we look in detail at the photoemission process, what's occurring in our material is that the X-rays from their source can ionize atoms in our material and produce photoelectrons. And the photoelectrons' energy is then the energy that binds them in these filled orbitals around the nucleus of an atom. And the energy of the photoelectrons is expressed as binding energy, and that's calculated from the energy of the photons. So for aluminum K-alpha X-rays, that's 1486 eV. The kinetic energy of the photoelectrons, so that's what we measure with our electron spectrometer, and that can be tens to hundreds of eV. And then the work function of the spectrometer, and that's the amount of energy that is required to get the photoelectrons from our solid material out into the vacuum of the instrument so that they can be collected and analyzed. So when we look at spectra, we'll present this as plots of the binding energy of the photoelectrons versus the electron intensity. And this particular spectrum is of a clean copper foil. So all we're going to see is photoelectron peaks from the copper itself. But as you can see, we see multiple peaks because there's multiple filled electron orbitals in copper atoms. So we see the 3D, 2p and 3s peaks, and then the 2p and the 2s peaks, all filled core level shells of these atoms. And as you get higher in quantum numbers, you see spin orbit splitting and other effects that affect both the position, the shape, and the splitting of the peaks. You also see Auger peaks in a photoelectron spectrum. Auger is a competing process for generating electrons from samples, and these electrons have similar energies as photoelectrons, so you will see them in the same spectrum. But we're going to focus on the photoelectron peaks. So why is photoelectron spectroscopy surface sensitive? Well, the photoelectrons produced in this process have kinetic energies of, say, tens up to around 1,000 eV. And the inelastic mean free path of electrons with those low energies in solid materials is typically only a few nanometers. So any photoelectrons that are produced deeper into a sample cannot escape the sample without undergoing scattering. And so if you look at the spectrum and you see these changes in background at various energies, those are actually photoelectrons that aren't being emitted with characteristic energies, but rather have been scattered inelastically in the sample, lost energy, and appear as just background signals. So only the photoelectrons being produced in those outer few atomic layers on a sample are able to escape and be analyzed by our spectrometer and appear as peaks in our spectrum. The most valuable features of XPS is its versatility and the wealth of information you can get from a sample. So not only are you able to do an elemental analysis to see what elements are present on the surface, you can also determine the chemical states of many of those atoms, their oxidation states, their chemical bonding, and so forth. You can also etch into a sample to perform what's called a depth profile, and I'll show you an example of that in a bit. Finally, you're able to map the distribution of certain materials on the surfaces of the sample. So this versatility is one of the reasons why XPS is very widely used for industrial analysis. For the remainder of today's webinar, I'd like to go through one case study that used many of the features available from XPS to analyze a client sample and determine the cause of poor wire bonds. So this particular client was performing wire bonds to an IC. And so this is the IC here mounted in its housing, and you can just see these thin aluminum wire bonds going to the pads on the surface of the IC. And the problem was that some dyes had good bonding, some had bad, but the client was able to supply both good and bad samples for analysis. So these are SEM images showing these bonds. So this is the wire coming in, and here's the aluminum bond pad. So it's an aluminum wire bonding to an aluminum pad, and these are wire bonded, and then they perform pull tests to see how strong the bond is. So this is a good sample where the pull test passed. The wire was not pulled off the pad after bonding. This is an example of a poor bond where the wire was present after bonding, but during the pull test, it came off the surface. So the question is there something different about the surface chemistry of a good sample versus a bad sample that would explain the difference in pull test results and the performance of the wire bond? Samples of the poor performing wire bond pads and the good performing wire bond pads were placed into our XPS instrument for analysis. The spectra shown in this plot are from one area on a poor pad and one area on a good pad. And we plotted binding energy of the photoelectrons versus photoelectron intensity. And the position of the peaks tells us which elements produce these photoelectron peaks. And so we see the expected peaks from aluminum and oxygen. So these are aluminum wire bond pads exposed to the air, so they have a native oxide layer on them. But we also see a large difference in the amount of carbon on the poor pads versus the good pads. with a large amount of carbon showing up on the pore pads. And although the photoelectron peak is rather impressive, this is still a very thin film. Because we can see the aluminum peaks through this film, if it's continuous, for some analyses, this probably would be sufficient information to say there is a contaminant present on the pore pads, and I'm going to try and eliminate that contaminant to get better performance. But for this particular client, we were asked to do more work to try and identify further the type of contaminant and how much was present. In order to determine how much of the carbonaceous contaminant was present, a total of 18 good pads and 18 poor pads on a number of different dyes were selected and analyzed, and then the spectra were quantified using standards. This table shows the results. One thing to remember is that the quantification of XPS data produces normalized results, so the results will add up to 100%. So in the case of the pore pads where you have a large amount of carbon, that actually attenuates the signal from the aluminum and oxygen underlying the carbonaceous layer. But you can see the dramatic difference between the good pads and the poor pads, and also that the results are fairly consistent. All the good pads have low carbon, all the poor pads have high carbon. As we mentioned previously, XPS can also provide chemical state information on certain materials. So this is a reference spectrum of mylar plastic. And you can see if you look at high resolution at the carbon photoelectron peak, the carbon photoelectrons will have slightly different energy determined by their chemical bonding. So carbon-carbon photoelectrons will have slightly lower energy than carbon bonded to oxygen, and carbon bonded to two oxygens in an ester or acid functional group will have even higher energy. So we can use this information to determine at least something about the structure of this particular material. So if we look at the carbon photoelectron peak from the contaminant we identified on the poor aluminum wire bond pads, we can see that the carbon is in a couple different chemical states. So the main carbon peak here is from a hydrocarbon type carbon-carbon or carbon-hydrogen bond, but we also have this distinct peak from a carbon photoelectrons coming from an ester or acid functional group. So this allows us to say that the contaminant does contain an ester or an acid functionality. And so it's not going to be as specific as vibrational spectroscopy, where we could maybe identify even more specifically what the material was. But the big advantage is that we are able to do some chemical analysis on these very, very thin layers that would be impossible to analyze with FTIR. So far we've been able to identify that there is a contaminant present on the poor wire bond pads. It seems to be consistently present on the poor pads and not on the good pads. We know approximately how much material is present, and we know something about its chemistry. It contains an ester or an acid functional group. Another question we'd like to answer is how thick this contaminant is. And in order to do that, we're going to have to etch into the sample. Because XPS is so surface sensitive, at any one time we're only seeing the outermost atoms, but we were able to etch those off and look at underlying material. We could build up what's called a depth profile into the sample. So I think about this as analogous to reading a book. You can only see what's written on the topmost page, but if you had a way to turn the page and expose the next page in the book, you could then build up an entire story by sequentially etching into a material. This analysis technique is called depth profiling, and this diagram will illustrate the process. So this is sort of a generic diagram showing that you have a source irradiating your sample, a detector to detect your signal coming out, and then what you're going to add for this experiment is an ion gun to etch into this material. So in this case we have a multi-layered sample, And we're only analyzing the exposed layer on the surface. But if we're able then to etch into the material, as we expose the underlying layers, we can build up a profile of the material into the depth of the sample. So we're going to present the sputtering time with the ion gun, which could also be converted to a depth with the proper standard, versus the intensity. And as we etch into it, we expose, in this case, the layers that we've colored in gold and yellow to build up our depth profile over time. So these are depth profiles from one area on a good wire bond pad and one area on a poor pad. So if we start with the good pad, here we've plotted the depth into the sample versus the atomic percentage, and we've measured 3 different elements: oxygen, aluminum, and carbon. So as we suspected from our previous results, carbon is low throughout the entire profile. We don't see an enhancement or very little enhancement of carbon on the surface of the sample. What we do see is an oxide layer. Again, this is a native oxide layer formed from exposure of aluminum to the atmosphere, and it's a couple nanometers thick. So as we sputter into the sample, oxygen is high throughout the oxide layer, and then we break through the oxide layer, oxygen goes down, aluminum goes up. The profiles aren't extremely sharp because remember the surface of this pad is rather rough, and that's why you don't get a step profile but a little bit of smearing. In contrast, if you look at the poor pad, as we suspected, we see a layer rich in carbon, and it's around 1 to 1.5 nanometers in thickness. And we can see there's also oxygen that we're picking up, both associated with that carbonaceous layer, because we know there's an ester or acid functional group included, and maybe some of the oxide layer associated with the aluminum surface. So once we sputter through the carbon layer, then we see the oxide layer that we would expect from an aluminum metal surface, and then eventually we sputter through that and the aluminum metal is exposed, oxygen and carbon goes down. So from this analysis, we can say that the thickness of this carbonaceous film on the surface of these wire bond pads is less than 2 nanometers thick. To summarize the results from our experiment, we were able to determine that the poor wire bond adhesion on these aluminum pads is caused by a contaminant. It's organic in nature, and it does contain an ester or acid functional group. It's less than 2 nanometers in thickness, and it's very consistent. The levels on the poor pads are consistent, and the absence of this contaminant on the good pads is very consistent. So from this information, the client was actually able to identify the material or the source of the material as an ester-based lubricant being used in the facility, and efforts made to control that lubricant and reduce the background levels did result in more consistent wire bond performance. I hope today I've been able to give you some idea on how you can use surface analytical techniques to probe the very outermost layers on solid materials to answer questions involving the chemistry going on with just a few atomic layers on the surface. Probably the most commonly used of these techniques is X-ray photoelectron spectroscopy, and it can provide elemental analysis, chemical state analysis, and depth profiles of materials. One area we didn't get a chance to talk about today, but it also can map the distribution of materials on surface. And the many industrial and research applications include any time two surfaces interact or a surface interacts with a heterogeneous liquid gas material. Well, thank you very much for joining us today. I enjoyed speaking with you, and I would be happy to answer any questions you might have. Okay, so our first question is, can XPS identify the compound at the surface? For instance, can it identify Al2O3? And the answer to this is yes. In many cases, it can identify specific oxides or other compounds, particularly for inorganic materials. It is very useful for that. The example in the webinar was of a carbonaceous material, and as you saw, it's not particularly specific for those materials, but in many cases for oxides and inorganic compounds, it can be much more specific in identifying certain phases. So thank you. The second question is spot size and resolution. And the spot size of XPS, typical spot sizes we'd use would be anywhere from 10 micrometers up to around a millimeter in size. Below 10 micrometers, it's possible to sometimes acquire data on major elements, but you're really limited in the amount of signal you're going to get out. Resolution, I think we're referring here to spatial resolution, and again, this would be particularly important if we were doing mapping applications. So if you're mapping major elements, you can again get down to a spatial resolution of about 10 micrometers on surfaces. Third question, how is this technique used for glass delamination of vials? Great question. So this is an area that we've done a lot of work on, and typically what we're using XPS for is not looking at the glass flakes that are generated by delamination, but rather looking at the surface chemistry of the interior surface of the vials. And that can be an indication of what happened to produce the corrosion and eventually delamination of glass. So looking at things like how the chemistry has been altered by exposure to the material in the vial. Also, a big area would be looking at how surface treatments have been applied to the vials and whether they were effective. And so for XPS, it's best used on bulk solid samples. So the focus there would be on the interior surface of vials for delamination studies. Next question was, what kind of lateral resolution does XPS have in terms of mapping? Also, well, for mapping, this is similar to our previous answer in that the effective resolution goes down to about 10 micrometers. If you try and go below that, it really is limited to mapping major elements that have a large difference in concentration across the surface. You can do larger areas too, up to millimeter sizes, and get effective maps that way. And of course, this is if you're mapping using the X-ray beam. You also, in some cases, have the possibility of doing stage mapping, which would allow you to do even larger areas. But the minimum size and resolution that we have found effective is about 10 micrometers. Okay, next question was, how long roughly does each measurement take in reference to samples being susceptible to oxidation? Okay, so one thing I didn't really talk extensively about, but because you're analyzing these very thin layers on surfaces, you need to maintain the cleanliness of your surface in an ultra-high vacuum chamber. So typically XPS is performed in chambers with very good vacuum, below 1 × 10⁻⁹ torr. So that allows you to have a significant amount of time to analyze your samples without danger of oxidation. So at a pressure of 1 × 10⁻⁶ torr, if every atom or molecule that hit a surface sticks and reacts, you would form a monolayer of material in 1 second. So if you can reduce the pressure in your chamber to 10⁻⁹ torr, now you have 1,000 seconds or 15 minutes to do the analysis. So that defines the typical analysis times for a lot of samples. It may be around 15 minutes to up to an hour, say, to get a good spectral characterization. Now, if you're doing an analysis like a depth profile or a mapping experiment and looking at minor elements, then your times will be extended because you have to collect multiple spectra if you're doing a depth profile, or move your sample underneath the X-ray beam or scan the X-ray beam for mapping purposes. So basic answer would be anywhere from 15 minutes to an hour per sample for the analysis.
That does it for the questions. Thank you again for attending today's webinar. Please visit McCrone.com for a schedule of our future webinars.